The oldest photograph in existence shows a newborn universe. This is the cosmic microwave background, the first light released after the Big Bang, and it contains a hidden code. By the end of this journey, you will understand how to read this ancient map and what its strange imperfections reveal about reality itself. Why does this baby picture of the cosmos seem to point a mysterious finger in one specific direction? What could a giant cold spot, a cosmic bruise, possibly tell us about other universes? We are about to become detectives, sifting through the faintest whispers of creation to question everything we think we know. What does it feel like to hold a message from the dawn of time? This primordial glow is not a simple, featureless fog. It is a photograph, and like any photograph, its true story lies in the subtle details hidden within the grain. For decades after its discovery, this cosmic afterglow was thought to be perfectly smooth, a uniform whisper from the beginning of everything. That smoothness was the puzzle. A perfectly uniform infant universe should have remained a formless cloud of gas, with no way to gather into the magnificent structures we see today, the galaxies and clusters that paint the darkness. The seeds for everything had to be there, imprinted on that first light. The challenge was to develop the film. We needed a camera sensitive enough to detect the faintest variations in this ancient radiation, variations of just 1 part in 100,000. That is like trying to measure the difference in height between a perfectly smooth sidewalk and one with a single grain of sand resting on it. The quest to build this camera led scientists to the most remote and silent places on Earth, high on mountain peaks and in the dry, still air of the Antarctic plateau, places where the interference of our own world fades to a minimum. From these silent outposts, we began to develop the universe's baby picture, and what emerged was not a featureless blank, but a map of the cosmos at its birth, speckled with tiny, vital imperfections. These are the cold and warm spots in the microwave sea, and they are the genetic blueprint for all of existence. These tiny imperfections are the universe's first whisper of structure. But to hear that whisper clearly, we had to build ears of unimaginable sensitivity. The story of mapping the cosmic microwave background is a tale of human ingenuity confronting a signal so faint it borders on silence. It began not with a grand telescope pointed at stars, but with strange, purpose-built instruments designed to listen to the cold emptiness of space itself. The first major leap came from the ground, from places like the Atacama Desert in Chile. Here, the air is so high, dry, and still that it interferes very little with the delicate microwave signal from deep space. Giant white dish antennas, like the ones at the Atacama Cosmology telescope, act as colossal ears, patiently collecting photons that have been traveling for over 13 billion years. But the true revolution in clarity came when we left Earth's atmosphere behind entirely. Spacecraft like NAS, a Wilkinson microwave anisotropy probe, known as WMAP, and the European Space Agency's Planck satellite became our ultimate eyes in the void. These are not cameras in any ordinary sense. They are packed with devices called differential microwave radiometers and bolometers. Think of a bolometer as the most sensitive thermometer ever conceived. It is designed to absorb the energy of incoming microwave photons and measure the infinitesimal amount of heat they generate. We are talking about detecting temperature differences of mere millionths of a degree across the sky. To achieve this, these instruments are cooled to temperatures within a fraction of absolute zero, colder than the depths of interstellar space itself, just to ensure their own heat does not drown out the cosmic signal. The mission of these satellites was a slow, meticulous dance. They did not simply take a snapshot. They spent years slowly spinning and scanning, pixel by microscopic pixel, building a map of the entire celestial sphere. But the raw data they sent back was not a clear picture. It was a cacophony. The faint CMB signal was buried under a roar of foreground noise, the radio buzz of our own Milky Way galaxy, the glow of interstellar dust, and the emissions from distant galaxies. Separating the cosmic whisper from this galactic static is like trying to hear a single violin in a symphony orchestra while standing outside the concert hall. It requires brilliant software and statistical techniques to digitally subtract each layer of interference, peeling back the foregrounds to reveal the pristine background beneath. The final product of this multi-year effort is not a single image you can simply look at. It is a dataset of staggering precision, a full sky map of temperature variations rendered in a palette of color, where deep red might represent a region a few millionths of a degree warmer than the average blue. This map is the ultimate treasure. It is the cleanest, most detailed baby picture of the universe we will likely ever have. But a map is just a collection of dots. The real magic, the moment we learn to read the hidden language of the cosmos, begins when cosmologists take this map and ask it questions. They apply the tools of statistics, looking for patterns in the arrangement of those hot and cold spots. Is their distribution random, or is there a hidden order, a signature of the universe's fundamental laws written into its first light? With this map in hand, we are no longer just looking at a picture. We are holding the original manuscript of creation, and now we must learn to decipher its text. The map of the cosmic microwave background is our most powerful scientific instrument. To read it, we first need to know what we are looking for. What should the blueprint of a healthy, newborn universe contain? For the last few decades, cosmology has been guided by an elegant and incredibly successful framework known as the lambda cold dark matter model. This is our standard playbook for the cosmos. It tells us the universe is made of about 5% ordinary matter, the atoms that build stars and planets, about 27% mysterious dark matter that provides the gravitational scaffolding for galaxies, and about 68% dark energy, a force causing the expansion of space to accelerate. This model makes a very specific prediction about what the patterns in that ancient light should look like. To understand that prediction, we need to travel back to the universe's first 380,000 years. Picture it not as empty space, but as a searing, opaque ocean of plasma, a roiling soup of particles and light. In this dense medium, gravity was constantly trying to pull matter together into clumps, while the intense pressure of radiation was trying to push it apart. This tug-of-war set the entire cosmos ringing like a bell. Regions would compress under gravity, heating up, then the radiation pressure would blast them apart, causing them to expand and cool. These were literal sound waves traveling through the primordial plasma. Then, in an instant, the universe cooled enough for atoms to form. The fog cleared. The light which had been trapped was suddenly set free. At that precise moment, those sound waves were frozen in place. The compressions, the hot spots, and the rarefactions, the cold spots, were imprinted onto the light like a phonograph recording. This is why the CMB map is not a random scatter of dots. It shows rings, subtle concentric patterns of slightly warmer and cooler regions. These are the echoes of those first cosmic notes, the acoustic oscillations. When cosmologists analyze the map, they translate it into something called a power spectrum. Think of it as a cosmic ruler. It measures how common spots of different sizes are. The standard model predicts a very specific set of peaks and valleys in this graph. The first major peak tells us the universe is geometrically flat. The second peak reveals the amount of ordinary matter. The third relates to dark matter. The fact that the real CMB data matches this predicted pattern with breathtaking precision is one of the greatest triumphs of modern science. It gave us a precise age for the universe, confirmed the existence of dark energy, and provided a detailed inventory of cosmic contents. For a while, it seemed the case was closed. We had a theory that explained nearly everything we saw, but a map this precise is also a strict judge, and when scientists looked past the beautiful agreement of the peaks and valleys, when they examined the map itself with forensic detail, they began to notice a few faint smudges on the blueprint. Features so subtle they could be dismissed as noise, yet so persistent they whispered of something the standard model had not accounted for. The map was agreeing with the theory in chorus, but in a few quiet corners, it seemed to be humming a slightly different tune. The blueprint of the cosmos, it seems, contains a faint but deliberate smudge. When cosmologists finished cleaning the data from those magnificent space telescopes, they expected a map of perfect randomness, a celestial fingerprint with no preferred orientation. The fundamental assumption of modern cosmology, the Copernican principle, insists the universe has no center and no edge. From any vantage point, the large-scale structure should look essentially the same. There should be no up, no down, no left, no right in the grand scheme of things, but the map whispered otherwise, as researchers performed intricate statistical analyses, decomposing the sky into mathematical components called multipoles. They found something deeply unsettling. The very largest patterns in the cosmic microwave background, the broadest warm and cool swaths stretching across billions of light years, were not oriented randomly. They showed a curious alignment, a kind of cosmic grain, as if the universe had a subtle preferred direction. Even more bizarrely, this alignment seemed curiously linked to our own backyard. The so-called axis of this pattern pointed eerily close to the plane of our solar system. Scientists, with a mix of dread and dark humor, named it the axis of evil. The name captures the profound threat it poses to our foundational ideas. This is not a small detail. Teams working independently with data from both the WMAP and Planck satellites have confirmed the anomaly. The probability that such an alignment would occur by pure chance in an isotropic universe is extraordinarily low, something like flipping a coin and getting heads 20 times in a row. The immediate suspicion, of course, is that we are seeing our own reflection. Could some unknown emission from within our solar system, some subtle cloud of dust or magnetic field, be contaminating the signal? Yet, after years of the most painstaking forensic work, subtracting every conceivable foreground, the alignment stubbornly remains. It lingers in the cleanest data we have like a ghost in the machine. If it is not an artifact of our measurement, then the implications are staggering. It would mean that on the largest scales we can observe, the universe remembers a direction. And that direction, by a staggering coincidence, is aligned with the humble plane in which Earth orbits the Sun. This strikes at the heart of the Copernican idea. It suggests our position in the cosmos might not be entirely random, that we may, in some faint but measurable way, be linked to the universe's deepest architecture. Could this axis be a fossil, a scar from a time before the Big Bang, a structural spine left over from some earlier phase of reality? Or is it a shadow cast by something immense and unknown lying beyond the horizon of our observable universe? The axis of evil does not give us answers. It simply points a silent, unwavering finger into the darkness, demanding we question a truth we thought was sacred. While the axis of evil challenges our place in the cosmos, another feature on the map defies explanation through sheer cosmic emptiness. In the southern sky, there is a patch of the cosmic microwave background that is not just cool but profoundly, inexplicably cold. This is the cold spot, a region spanning nearly 1 billion light-years where the ancient radiation is significantly chillier than our models predict. If the CMB is the universe's baby picture, this is a distinct pale bruise on its skin, a blemish that refuses to fade. The most straightforward explanation cosmologists have proposed is a cosmic supervoid. Imagine the large-scale structure of the universe as a vast cosmic web, with dense filaments of galaxies surrounding enormous, empty bubbles. If one of these immense voids happened to lie directly along our line of sight to the CMB, its effect could, in theory, create a cold spot. Here is how it would work. As light from the cosmic microwave background travels toward us through billions of years of expanding space, it climbs out of gravitational wells. When light climbs, it loses energy, stretching to longer, redder wavelengths, an effect called the integrated Sachs-Wolf effect. But if that light passes through a truly vast region of nothingness, an underdense supervoid, the opposite happens. The void itself is a kind of gravitational hill. As light enters it, it actually gains a tiny bit of energy, becoming slightly hotter. Then, as it exits the far side of the void, it loses that energy again, becoming colder. The net result after this long journey could be a detectable cold imprint on the map. It is a beautiful, elegant idea. There is just one monumental problem. To produce a cold spot of the size and intensity we observe, this void would need to be staggeringly large, perhaps one of the largest structures in the entire observable universe. And when astronomers point their telescopes to that exact patch of sky to count galaxies and map the cosmic web, they do find voids, but nothing on the colossal scale required. The observed emptiness is significant, but it is not nearly empty enough to explain the profound chill. The data from galaxy surveys simply does not match the supervoid theory's demands. This leaves us with a mystery that invites more speculative and far more thrilling possibilities. One radical idea is that the cold spot is not a feature of our universe at all, but the shadow of a collision with another universe. During the period of hyper-fast expansion known as cosmic inflation, our entire observable cosmos may have been just one bubble in a frothing multiverse. If an adjacent bubble universe brushed against ours during this early phase, the energy of that collision could have left a permanent scar on the fabric of space-time, a region where the primordial plasma was subtly disturbed, cooling the light that eventually escaped. Another possibility points to a flaw in the very geometry of reality, a topological defect like a cosmic texture, a knot in the fields that govern the universe that unraveled in the early moments, leaving behind a distinct temperature imprint. The cold spot persists, a quiet, cold anomaly on our most precise map of creation. It is too large to ignore, yet too elusive to explain with the comfortable pieces of our standard model. It does not point a finger like the axis of evil. It simply sits there, a profound absence that whispers of either a cosmic coincidence of unimaginable scale or a crack in the door to a physics we have yet to imagine. The principle of cosmic fairness faces its most direct challenge yet. Beyond the mysterious axis and the profound cold spot, the map of creation reveals a third, deeply unsettling quirk. Our universe on its grandest scale appears to be lopsided. This is the anomaly of hemispherical asymmetry, and it asks a simple, radical question. What if one half of the cosmos is fundamentally different from the other? The standard model of cosmology is built on a bedrock assumption called isotropy. It means the universe, when averaged over vast distances, should have no favorite direction and no special location. The properties of space and the rules of physics should be the same everywhere. The cosmic microwave background is our ultimate test for this idea. It is a snapshot of the entire observable universe at a single moment in its infancy. If isotropy holds true, then this snapshot should be statistically identical no matter which way you look. The pattern of hot and cold spots, the level of detail and lumpiness, should be evenly distributed across the sky like a perfectly mixed batter. But when scientists from the Planck collaboration performed an exhaustive statistical analysis, slicing the sky into hemispheres and comparing their power, they found something was off. The technique involves a mathematical dissection of the map, measuring the statistical strength or power of the temperature fluctuations in one half of the sky versus the other. The result was not a dramatic split, but a persistent, subtle bias. one celestial hemisphere, roughly centered on a direction in the constellation of Vulpecula, shows fluctuations that are about 10% more powerful than in the opposite hemisphere. In simpler terms, one half of the infant universe was slightly more lumpy, more textured than the other. The probability that this imbalance arose from random chance is less than 1 in 1,000. This is not a smoking gun, but it is a consistent, nagging signal that refuses to be ignored. Imagine taking a photograph of a vast, calm ocean at dawn. You would expect the pattern of waves to be essentially random, with no reason for the waves on the left side of the photo to be consistently taller than the waves on the right. The CMB asymmetry suggests that in the universe's first photograph, the waves on one side are, in fact, subtly but measurably taller. What could cause such a fundamental imbalance at the birth of everything? One possibility points to the mechanism of cosmic inflation, that brief period of hyper-fast expansion thought to have smoothed and shaped the early cosmos. The simplest models of inflation are beautifully symmetric, like a single, perfect balloon inflating at an unimaginable rate. But the asymmetry hints that this inflation may not have been so uniform. Perhaps the inflationary field, the engine of this expansion, was not a single, smooth entity. It could have been tangled, or there could have been multiple fields influencing each other, creating a kind of texture in the expansion rate itself. In this scenario, one region of the primordial universe might have inflated just a fraction more, or under slightly different conditions than another, imprinting a subtle difference in the strength of those initial quantum fluctuations that became the seeds for galaxies. Another, more profound interpretation is that the asymmetry is not a relic of uneven expansion, but a clue to the true shape of reality. It suggests the universe might be anisotropic at its core, born with a fundamental lopsidedness woven into the fabric of spacetime. This would mean the constants of nature, or the very behavior of space, could have had a gentle gradient from one region to another in those first moments. While the data shows the modern universe is exquisitely uniform, this fossilized asymmetry in its first light whispers that the initial conditions were not perfectly even. It is as if we found an ancient stone tool with one edge deliberately sharper than the other, telling us the maker had a specific intent, a handedness, that influenced the creation from the very start. The hemispherical asymmetry does not overturn our cosmology, but it etches a question mark over its simplest story. It suggests the dawn of time may have been a more complex, textured event than we once believed, a beginning with a subtle tilt that we are only now learning to see. The map of creation is missing its grandest features. When we look at the cosmic microwave background, we expect to see a certain rhythm in the sizes of its patterns, from the tiny specks that seeded galaxies to continent-sized warm and cool regions that stretch across the sky. There is a mathematical expectation for how these patterns should relate to one another over different distances, a concept cosmologists call angular correlation. In essence, if you pick two random points on the CMB map separated by a certain angle, the standard model predicts how likely their temperatures are to be similar. On small and medium scales, the map obeys this rule beautifully. But when scientists examine the very largest scales, corresponding to separations greater than 60 degrees on the sky, something strange happens. The correlation drops away almost to nothing. It is as if the universe forgot to draw its biggest waves. This missing large-scale correlation is often discussed in terms of two specific components, the quadrupole and the octupole. These are mathematical terms for the very broadest, smoothest patterns possible on a sphere, the cosmic equivalent of the first few notes in a chord that defines a song's key. In the music of the CMB, these low notes are curiously faint. They have less power, less prominence than all our theories insist they should. The probability that this is just a statistical fluke, a random quiet patch in the cosmic symphony, is low enough to make cosmologists deeply uneasy. What makes the puzzle so compelling is its persistence. This lack of large-scale correlation was first hinted at in data from the COBE satellite in the 1990s. It was confirmed by the WMAP mission, and it remains stubbornly present in the exquisite, clean data from the Planck satellite. 3 generations of cosmic cartographers have all seen the same quiet sky on the grandest scales. So what could silence the largest possible vibrations of the infant universe? One radical possibility is that the universe is not infinite in extent. We always speak of the observable universe, the sphere of light that has had time to reach us since the Big Bang. But the true, full universe could be larger, or it could be finite and shaped in a way we do not yet perceive. If the cosmos has a complex topology, if it is folded back on itself in some multidimensional shape like a cosmic donut, then there is a natural limit to the size of waves that can exist within it. Just as a guitar string can only vibrate at wavelengths that fit its length, a finite universe would have a maximum wavelength for its primordial oscillations. The missing large-scale correlations could be the direct signature of that cosmic scale, a cutoff point where the waves simply cannot exist because the universe is not big enough to hold them. We would be seeing in the oldest light the geometric walls of our own cosmic room. Another, equally profound explanation looks not to the size of the universe but to its very first moments. The period of cosmic inflation is thought to have stretched a microscopic patch of space-time into our entire observable cosmos, amplifying quantum fluctuations into the seeds for structure. But what if inflation did not start from a perfectly smooth, featureless state? What if there was a pre-inflationary era, a brief time before the hyper-expansion began, where the universe was already textured with its own ancient imprinted patterns? When inflation then stretched this pre-existing canvas, it would have smoothed out most features, but the very largest ones, the ones that were already cosmic in scale, might have survived the process only in a muted, diluted form. The faint quadrupole and octupole we see today could be the faded ghosts of that pre-inflationary epoch, fossils from a time before time as we understand it began. They would be whispers from the universe's true birth before the inflationary bell was rung. This missing correlation is not a flashy anomaly like a cold spot or a pointed axis. It is a profound stillness, an unexpected hush in the cosmic background hum. It tells us that on the grandest canvas we can observe, the brushstrokes of creation are fainter than they should be. Whether this points to a finite cosmos or an echo from before the beginning, it is a quiet reminder that our map, for all its detail, may still be missing the borders of its own page. The universe's baby picture is a silent symphony, and to hear its individual notes we need a special kind of ear. Cosmologists do not just stare at the map's colorful swirls. They translate it into a new language, the language of spherical harmonics. Think of this as the ultimate tool for cosmic listening. Imagine you are hearing a rich, complex chord played on a piano. Your ear can appreciate the overall sound, but to truly understand it, you need to break it down into its fundamental frequencies, the individual notes that combine to create that unique harmony. Spherical harmonics does exactly this for the sky. It takes the entire celestial sphere with all its intricate hot and cold spots and decomposes it into a set of fundamental patterns, each with a specific angular size. The simplest pattern is called the monopole. This is not a pattern at all, but the average temperature of the entire sky, the single, constant note that is the background hum of the cosmos, about 2.7 degrees above absolute zero. The next is the dipole. Picture a pattern where one half of the sky is uniformly warmer and the opposite half is uniformly cooler. This dominant signal is not from the ancient universe but from our own motion. Just as you feel a wind if you run through still air, our solar system is moving through the sea of cosmic radiation, creating a warm spot ahead of us and a cool spot behind. It is the universe's way of telling us we are not standing still. After we subtract these first two notes, we reach the true cosmic music. The quadrupole represents patterns with two hot and two cold regions, like a simple checkerboard stretched across the sky. The octupole has 8 such regions. As we go to higher multipoles, the patterns become finer and finer, corresponding to smaller and smaller hot and cold spots on the map. The entire CMB sky is the sum of all these multipole patterns combined, from the broadest strokes to the tiniest specks. But how do we know which notes are loud and which are soft? This is where the power spectrum comes in. It is the cosmic equivalent of a sound engineer's frequency analyzer. On one axis, it plots the multipole number, which corresponds to angular scale. On the other axis, it plots the power or amplitude of that particular note. The result is a graph with a series of distinct peaks and valleys, a cosmic barcode. The height of the first peak tells us the universe is geometrically flat. The second peak reveals the density of ordinary matter. This graph is the quantitative heartbeat of the Big Bang model, and its stunning agreement with prediction is a triumph of modern science. But this precise language is also what allows us to identify the whispers that do not fit the melody. The axis of evil is a story told in the unusual alignment of the lowest multipoles. The hemispherical asymmetry appears as a difference in power when we compare the spectrum of one half of the sky to another. The lack of large-scale correlation shows up as those first few bars on the graph being curiously quiet. By speaking this mathematical language, we move from saying the map looks a little odd to being able to state, with statistical rigor, that certain features have only a 1 in 1,000 chance of occurring in a standard, random universe. This is how a faint smudge on a photograph becomes a genuine cosmic anomaly, a quiet but persistent note in the symphony that suggests the music of creation may have more verses than we once thought. These patterns are not cosmic accidents. They are a direct message from the quantum realm stretched across the sky. To understand the origin of those hot and cold spots, we must shrink our perspective down to a scale so small it defies imagination, to the very first fleeting moments after the Big Bang. In that inconceivably dense and energetic beginning, the universe was a seething sea of quantum fields. According to our best theory, one of these fields, dubbed the inflaton field, held a peculiar property. It possessed a kind of negative pressure, causing a repulsive gravity that sent space itself into a phase of hyper-fast expansion, known as cosmic inflation. For a fraction of a second, the universe doubled in size over and over again, faster than the speed of light, smoothing it out to the incredible flatness we observe. But here is where quantum mechanics leaves its permanent mark. Even in that primordial void, the inflaton field was not perfectly calm. At the quantum level, nothing ever is. Heisenberg's uncertainty principle tells us there is always a fundamental jitter, a tiny, random fluctuation in energy. Think of it like the surface of a perfectly still pond on a windless day. Even in total calm, if you look closely enough, you will see a faint, ceaseless shimmer caused by the quantum motion of the water molecules themselves. In the infant universe, these were the quantum fluctuations in the inflaton field. They were unimaginably tiny, existing on scales far smaller than a single proton. Then inflation acted like the most powerful magnifying glass in existence. As space expanded at an exponential rate, it stretched those microscopic quantum jitters along with it. A fluctuation that was once smaller than an atom was, in less than a heartbeat, inflated to a size spanning thousands of light years. Where the field had a tiny peak of higher energy, inflation created a region of slightly higher density. Where it had a trough, it created a region of slightly lower density. These became the seeds of all future structure, the overdensities that would, over billions of years, pull in matter through gravity to form galaxies and clusters. Crucially, inflation makes a very specific prediction about the character of these seeds. Because the expansion was so rapid and smooth, it should have imprinted a particular statistical signature onto the fluctuations. They should be nearly scale invariant. This means that whether you look at patterns the size of a galaxy cluster or patterns the size of a supercluster, the relative strength of the fluctuations should be almost the same. It also predicts they should follow a Gaussian or random bell curve distribution. When cosmologists analyze the CMB map, this is precisely what they find with breathtaking precision. The pattern of hot and cold spots matches the predicted statistical fingerprint of quantum noise blown up to cosmic proportions. This is the smoking gun evidence for cosmic inflation. It tells us that the largest structures in the universe owe their existence to the smallest possible vibrations in the fabric of reality. Yet for all its success, the inflationary model remains a framework. We have confirmed its predicted outcome, but we know almost nothing about the actor, the inflatoned field itself. What was its nature? What ended inflation? The subtle anomalies in the CMB map, the axis, the asymmetry, the missing correlations may be vital clues here. They hint that the story of inflation might be more complex than the simplest, smoothest models suggest. Perhaps inflation was driven not by one field, but by several interacting fields, a scenario called multi-field inflation. This could create additional textures and asymmetries in the density patterns. Or perhaps the inflationary potential, the landscape the field rolled down, had a sudden turn or a step, a feature that would leave an imprint on the largest scales of the CMB. These anomalies are not necessarily contradictions. They might be the faint traces of inflation's richer, more detailed history, a quantum fingerprint with a few unique swirls we are only just beginning to discern. But the ancient light holds more than just a record of temperature. It also carries a hidden direction, a subtle alignment imprinted upon each photon like a watermark. This property is called polarization, and it opens a second, even more precise channel to the universe's first moments. To understand it, picture the primordial plasma just before the universe became transparent. It was a thick fog of free electrons and atomic nuclei, with photons of light constantly bouncing off those electrons in a process called Thomson scattering. Now imagine one of those photons approaching an electron. The electric field of the photon makes the electron jiggle, and as it jiggles, it re-emits the light. Crucially, this scattering process prefers light waves that are oscillating in a particular direction perpendicular to the electron's line of sight. As a result, the fog of plasma acted like a vast filter, imprinting a preferred orientation, a polarization, onto the light that finally escaped. The pattern of this polarization across the sky is not random. It is directly sculpted by the last motions of that electron sea before the atoms formed. Specifically, it is shaped by the velocity of the plasma, which was set in motion by those same primordial density waves, the sound waves ringing through the infant cosmos. This means the polarization map is not a separate picture. It is a dynamic movie still, capturing the direction and speed of the universe's material in its final moments of opacity. To decode this map, cosmologists look for two distinct types of patterns, which they call E modes and B modes, named for their mathematical resemblance to the electric and magnetic fields. E-mode polarization is the simpler, more common pattern. It looks like radial or concentric patterns centered on hot and cold spots, a direct signature of those density fluctuations pushing and pulling the plasma. Its detection was a major triumph, providing beautiful, independent confirmation of the temperature map story. But the true holy grail of CMB science lies in the hunt for the other type, the B-mode polarization. This pattern has a swirling, curling character, like the pattern of water going down a drain. It cannot be created by simple density variations. The only known mechanism in the early universe powerful enough to imprint such a curl onto the light is the passage of primordial gravitational waves. These are not waves in water or air. but literal ripples in the fabric of spacetime itself, predicted to have been generated during the violent frenzy of cosmic inflation. Think of inflation as a sudden, colossal shudder of spacetime. That shudder would have sent gravitational tremors echoing through the newborn cosmos, squeezing and stretching space as they passed. These ripples would have jostled the primordial plasma, imparting a distinct, swirling signature to the polarization of the CMB light. Finding a specific, predicted signal in the B modes would be the smoking gun for inflation, and more than that, it would allow us to weigh the inflationary energy itself. The strength of the B-mode signal tells us directly how powerful the inflationary field was, probing energies 1 trillion times higher than what the Large Hadron Collider can reach, taking us to the doorstep of a grand unified theory of physics. This quest has driven a new generation of experiments to the most extreme environments on Earth, like the South Pole Telescope and the Simons Observatory in Chile's high desert, where teams use arrays of thousands of superconducting detectors, chilled to a fraction of a degree above absolute zero, to hunt for this faint, curling whisper in the polarized sky. The search is extraordinarily difficult, as the inflationary B-mode signal is buried under foregrounds from galactic dust and subtle gravitational lensing effects that can mimic it. But the polarization map offers another profound opportunity. It provides a completely independent check on the strange anomalies we see in the temperature map. Does the axis of evil also appear in the polarization patterns? Does the hemispherical asymmetry show up there too? Early analyses suggest some of these features may have counterparts in the polarization data, making them harder to dismiss as mere artifacts or noise. If the universe's first light, in both its warmth and its directional alignment, tells the same strange story, then we are not just looking at smudges on a photograph. We are witnessing a consistent, fundamental feature of our origins, written in a dual language we are only just becoming fluent enough to read. The pristine whisper of the primordial universe is buried under a cosmic cacophony. To hear it, we must become forensic audio engineers, meticulously filtering out every source of interference from our own galactic neighborhood and beyond. The beautiful full-sky maps you see are not raw photographs. They are the final product of an exhaustive cleaning process, a digital excavation where scientists must separate the signal of creation from a symphony of modern cosmic noise. The first and most dominant source of this noise is our own Milky Way galaxy. It blazes across the microwave sky in 3 distinct ways. The first is synchrotron radiation. Throughout our galaxy, magnetic fields weave through space, and when high-energy electrons spiral along these magnetic field lines, they emit a broad, diffuse glow. This is the same physical process that lights up the jets of distant quasars, but here it is a fog emanating from our own galactic plane. The second is free emission. This comes from hot, ionized gas where electrons, freed from their atoms, scatter off atomic nuclei in a way that releases radiation. Imagine the faint, shimmering heat haze above a sun-baked road, but on a galactic scale. The third major galactic foreground is thermal dust emission. Microscopic grains of dust, warmed by starlight to just a few tens of degrees above absolute zero, re-radiate that energy in the microwave and infrared parts of the spectrum. This dust glow is not uniform. It traces the intricate filaments and clouds of our galaxy's spiral arms, painting complex patterns across the very sky we are trying to see through. But the foregrounds do not stop at the edge of the Milky Way. The distant universe contributes its own contaminating signals. Myriad distant galaxies, each emitting their own radio waves, appear as thousands of faint point sources that must be identified and masked. Even more significant is the effect of massive galaxy clusters. As the CMB light travels across the cosmos, a small fraction of it passes through these immense clouds of hot gas. Photons from the cosmic microwave background can collide with the energetic electrons in this gas, gaining a boost of energy in a process known as the Sunyaev-Zeldovich effect. This interaction creates a distinct, shadowy imprint on the CMB map, a slight dimple or a brightening that corresponds not to the ancient universe, but to these later giant structures. So how do we possibly clean this up? The key is that each of these foregrounds sings its song at a different pitch. The CMB itself has a very specific blackbody spectrum, a perfect thermal curve. Synchrotron radiation, dust emission, and all the others have wildly different spectral signatures. To exploit this, missions like Planck did not observe the sky at just one frequency. They scanned it simultaneously at 9 different frequencies, from radio waves up into the infrared. It is like listening to an orchestra with a set of 9 microphones, each tuned to hear only the violins, or only the brass, or only the percussion. By comparing the sky's appearance at all these different wavelengths, scientists can create precise mathematical templates for each foreground component. They can map the synchrotron fog, chart the dust clouds, and catalog the point sources. Then, with immense computational care, they subtract these templates away, layer by layer, like an archaeologist brushing dust from a fossil. This process is fraught with peril. Over-subtract a foreground, and you might erase a real, subtle feature of the CMB, perhaps even creating the illusion of a large, unusual cold spot. Under-subtract, and you leave behind galactic grime that could mimic a mysterious axis or asymmetry. Every claimed anomaly in the cosmic microwave background must pass through this forensic gauntlet. Researchers must prove, beyond a reasonable doubt, that the strange signal persists even in the cleanest possible map, after every known source of local noise has been accounted for. The fact that the axis of evil and the hemispherical asymmetry survive this ruthless cleaning is what makes them so compelling and so troubling. They are not dust on the lens. They appear to be etched into the film of creation itself. Every map, even one of the universe, contains patterns that are simply random noise. With millions of data points in the cosmic microwave background, we must expect a few strange shapes to emerge purely by chance, like seeing a face in the clouds. The critical task for cosmology is not just to find oddities, but to determine which ones are meaningful whispers from physics, and which are just the static of a vast, random dataset. This is the world of statistical significance, the mathematical filter that separates potential discovery from cosmic coincidence. To navigate it, scientists rely on 2 interconnected ideas, the sigma level and the p-value. Think of it this way: if you flip a coin 10 times and get 7 heads, that is not particularly surprising. But if you flip it 1,000 times and get 700 heads, you would rightly suspect the coin is weighted. The sigma level quantifies that suspicion. A 1 sigma result is mildly interesting, about a 32% chance of being a fluke. A 3 sigma result, where an anomaly deviates from expectation by 3 standard deviations, has only about a 0.3% probability of occurring randomly. This is where scientists start to get genuinely attentive. The gold standard in physics for announcing a discovery is 5 sigma. A 1 in 3.5 million chance that the signal is just noise. This was the threshold crossed for the discovery of the Higgs boson. Now, let us apply this lens to our cosmic anomalies. The axis of evil, that strange alignment of the largest patterns, typically registers around a 3 sigma significance. The hemispherical asymmetry and the lack of large-scale correlation also live in this intriguing but ambiguous 3 sigma neighborhood. They are persistent, they survive rigorous data cleaning, and they are unlikely to be random, but they have not reached the 5 sigma certainty that would force a rewrite of the textbooks. This statistical gray area is precisely what makes them such compelling mysteries. They are the universe hinting, not shouting. However, there is a crucial statistical trap known as the look elsewhere effect, or more formally, a posteriori statistics. If you search through enough data with enough freedom, you are guaranteed to find something that looks unusual. It is like checking every single cloud in the sky until you find one that looks exactly like a dragon, and then declaring dragons are a real meteorological phenomenon. The key to a robust discovery is prediction. If a theory predicts a specific, unusual feature in advance, and then we find it exactly where and how it was predicted, that carries immense weight. Many of the CMB anomalies, however, were not predicted. They were found by looking at the beautiful map and asking, does anything look odd here? This retrospective searching means the statistical bar for proof must be set even higher. A 3 sigma anomaly found after combing through the data might have a true significance closer to 2 sigma once the sheer number of possible comparisons is accounted for. This statistical lens is the sobering, essential filter for all cosmic mysteries. It tempers excitement with rigor, reminding us that the universe is under no obligation to make its secrets obvious. The anomalies in the ancient light pass the first test. They are unlikely to be mere noise, but the final verdict awaits either more precise data from future observatories or a brilliant theoretical prediction that explains exactly why these specific features must exist. Until then, they remain the most tantalizing questions on the map, the places where our standard model of the cosmos feels the gentle, persistent pressure of something it cannot yet explain. A persistent whisper demands we reconsider the blueprint itself. When the map of creation refuses to match our expectations, it is not the map that is wrong, but perhaps our interpretation of its legend. The strange features in the cosmic microwave background have become a catalyst for radical thought, pushing cosmologists to draft entirely new blueprints for reality. These are not minor tweaks to the standard model, but profound reimaginings of how the universe began and what shape it truly holds. One compelling line of inquiry focuses on the very engine of the beginning, cosmic inflation. What if that hyper-fast expansion was not perfectly smooth and uniform? This idea is known as anisotropic inflation. In this scenario, the inflattened field or the fabric of spacetime itself possessed a directional preference, causing space to stretch faster along one axis than others. Picture inflating a long, narrow balloon instead of a perfectly round one. The universe would have a subtly elongated geometry imprinted from its first instant. This directional stretching could naturally generate a preferred axis in the density fluctuations, potentially explaining the eerie alignment we call the axis of evil. The largest patterns in the CMB would carry the memory of that initial directional push, a fossil of the universe's first breath being a sigh in a specific direction. Another radical rethinking addresses the profound quiet on the largest scales, the missing correlations. Our standard model assumes the universe is simply connected, meaning if you travel in a straight line, you go on forever without ever returning to your starting point. But what if the cosmos is finite and multiply connected? Think of the geometry of a video game world, where if you walk off the right edge of the screen, you reappear on the left. The universe could have a similar, though far more complex, topology. It could be shaped like a 3-dimensional torus, a cosmic donut, or have other folded geometries. In such a finite, repeating space, there is a natural limit to the size of any wave or pattern. Just as a guitar string cannot vibrate with a wavelength longer than the string itself, the primordial sound waves in a finite universe would have a maximum possible size. The lack of large-scale correlation in the CMB could be the direct signature of that cosmic scale, the point where the waves simply hit the geometric walls of our celestial room. We would be seeing, in the oldest light, the fundamental shape of our universe, a hall of mirrors on a scale so vast we only perceive it as a curious silence. Perhaps the most profound alternatives look beyond the Big Bang entirely. The standard story begins with a singularity, a point of infinite density where our laws of physics break down. But some theories propose there was a before, One class of these ideas is bouncing cosmologies. In this view, our expanding universe is just one phase in an eternal cycle. A previous cosmos contracted down to a very dense hot state, but not an infinitely small point, and then bounced back outward in the event we call the Big Bang. That pre-existing, contracting universe would have had its own structure and history. When it bounced, it did not erase that information completely. The scars and textures of the old cosmos could have been imprinted in a diluted form onto the new one, setting the initial conditions that led to our observed anomalies. The large-scale asymmetry or the cold spot could be faint echoes of a universe that existed before our own. An even more exotic pre-Big Bang scenario comes from string theory, known as the ekpyrotic model. Here, our three-dimensional universe is envisioned as a membrane or brain floating in a higher dimensional space. The Big Bang is not a creation from nothing, but the result of a collision between our brain and a neighboring one. This titanic, slow impact would have generated heat and density, but the process is fundamentally different from inflation. It could produce a universe that is flat and uniform, but with a different statistical fingerprint in its fluctuations, one that might naturally lack the large-scale power that our standard model predicts. In this breathtaking picture, the cold spot could literally be a bruise from the collision, and the overall pattern of fluctuations a record of how the two worlds touched. These alternative cosmologies are not yet proven, and many face significant challenges, but their value is immense. They demonstrate that the faint smudges on our ancient map are not mere annoyances to be explained away. They are potential signposts pointing away from a comfortable, settled story and toward a far grander and more mysterious theoretical landscape. The universe's first light is not just a relic to be measured, but a riddle that may require us to reinvent our understanding of time, space, and origin itself. The map's strangest features may be messages from outside our own reality. This is where the cosmic microwave background collides with one of the most profound ideas in theoretical physics, the multiverse. If our universe is just one bubble in an eternally inflating sea of other bubbles, then perhaps the cold spot is not a bruise from within, but a fingerprint from a neighboring cosmos. The concept emerges from the leading theory of our own beginning, cosmic inflation. In many models, inflation is not a one-time event that started and stopped. Instead, it is eternal. The inflattened field, the engine of expansion, can decay in some regions to form stable, bubble universes like our own, while in the spaces between, inflation continues forever, constantly spawning new bubbles. In this infinite, frothing foam of universes, each bubble is a separate, self-contained cosmos with potentially different laws of physics. They are not floating in empty space as we understand it, but embedded in the still inflating background, separated by walls of incredibly high energy. Occasionally, in the frenzied expansion, two of these budding bubbles could drift close enough to touch. When they collide, it would be a cataclysm of almost unimaginable scale, a clash of entire realities. The collision would send a shockwave rippling through the interior of each bubble universe. For us, inside our bubble, that shockwave would manifest as a vast, circular disturbance in the primordial plasma, a region where energy was added or subtracted in a specific, symmetric pattern. This is the theoretical signature of a bubble collision, and it would leave a permanent mark on the cosmic microwave background. What would that mark look like? Physicists modeling these events predict it would create a distinctive, nearly circular pattern of temperature variation. The center of the circle would be either noticeably hotter or colder than the surrounding CMB, with the effect gradually fading toward the edges like a ripple on a pond. Crucially, this pattern would break statistical uniformity in a very specific way, creating a large, coherent feature that stands out against the otherwise random quantum noise. The cold spot, that billion-light-year-wide region of unexpected chill, fits this description intriguingly well. Its sharp edges and apparent coherence make it a candidate, though not a proven one, for such an exotic origin. The search for these signatures is now a serious, though needle in a haystack, endeavor within cosmology. Teams have developed sophisticated algorithms to scan the cleaned CMB maps for any telltale circular patterns that cannot be explained by standard physics or foreground noise. They look for temperature profiles that match the predicted shape of a collision's shock front. So far, no definitive, unambiguous collision signature has been found. The cold spot remains an anomaly, not a confirmation. The challenge is immense, as the signal would be incredibly faint after over 13 billion years of cosmic evolution, and it could be masked or mimicked by large-scale structures within our own universe. Yet the pursuit itself is revolutionary. It means we are using the oldest light in our universe as a telescope, not looking deeper into space, but peering sideways into the multiverse. A confirmed bubble collision signature would be the first empirical evidence for a reality beyond our own cosmic horizon. It would transform the multiverse from a philosophical speculation into a testable scientific framework. The cosmic microwave background would then be more than a baby picture. It would be a palimpsest, a document where the faded text of other universes might still be read beneath the primary story of our own. Every unexplained feature on that map becomes a potential window, a place where the walls of our bubble universe grew thin, and for a moment we felt the presence of another. The ancient light does more than reveal the universe's birth. It holds a detailed ledger of its entire future. The subtle patterns in that cosmic microwave background, the precise spacing and height of its acoustic peaks, are not just echoes of a primal sound. They are a complex equation where the only unknown variables are the darkest secrets of the cosmos, dark matter and dark energy. To understand how, we need to listen to the rhythm of that early cosmic slosh. Remember the infant universe as a plasma ocean ringing with sound waves. The distance these waves could travel in the 380,000 years before the fog cleared set a natural scale, a standard ruler imprinted on the sky. We see this ruler today as the apparent angular size of those first, strongest acoustic peaks in the CMB map. But how big that ruler appears to us depends on the geometry of the space between it and our eyes. This is where dark energy writes its signature. Dark energy, the force causing the expansion of the universe to accelerate, shapes the curvature of space-time on the largest scales. If the universe had high positive curvature like the surface of a sphere, light rays would converge, making that standard ruler appear larger. If it had negative curvature like a saddle, light would diverge, making it appear smaller. The exquisite data from the CMB shows the peaks at a specific angular size that corresponds to a universe with almost perfect flatness. This geometric flatness, a critical finding, tells us that the combined density of everything in the cosmos, matter and energy, must be at a very specific value. It is the first clue in the ledger. Then we turn to the ledger's second column, the relative heights of the peaks. The first peak is primarily a measure of the total density. But the second and third peaks are exquisitely sensitive to the composition of that density, specifically the balance between ordinary matter, made of atoms, and dark matter. Here is why. In the primordial plasma, ordinary matter and radiation were tightly coupled, locked in a push and pull. Dark matter, however, is invisible to light. It does not feel radiation pressure, it only feels gravity. So while the ordinary matter was being pushed outward by radiation pressure from a hotspot, the dark matter simply sat there, a gravitational anchor. This changed the rhythm of the oscillations. More dark matter meant a stronger gravitational pull back toward the center of the hotspot, altering the tone of the cosmic bell. The result is that the height of the second acoustic peak relative to the first tells us directly about the ratio of ordinary matter to dark matter. The CMB data gives us a clear number, ordinary atoms, the stuff of stars and planets and us, make up only about 5% of the cosmic budget. Dark matter, the unseen scaffolding, comprises about 27%. With total density fixed by flatness and the matter components now known, the remainder of the budget, a staggering 68%, must be in the form of dark energy, the component that dictates the expansion fate of the universe. This is how a snapshot of the universe's first moments becomes a prophecy for its entire lifetime. The map is a Rosetta Stone, translating the frozen sound waves of infancy into a precise inventory for all of cosmic history. This profound success makes the lingering anomalies on the map all the more tantalizing. If the standard model's ingredients are so perfectly measured, why do a few broad brushstrokes on the canvas seem misaligned or faint? Could the axis of evil or the missing large-scale correlations be subtle hints about the true nature of dark matter or dark energy themselves? Perhaps dark energy is not a perfectly uniform constant, but a field that varied slightly across space in those earliest times, leaving a directional imprint. Or maybe dark matter interacts with itself or with ordinary matter in ways more complex than our simple gravitational model, affecting the very largest waves in the primordial sea. The map's quiet whispers may be pointing toward a darker, richer story for the components that rule our cosmos. The silence of the ancient sky is about to be broken by a new chorus of listeners. While the maps from Planck and WMAP represent a monumental achievement, they are not the final word. They are the foundation upon which a new generation of cosmic cartographers is building, armed with instruments of almost unimaginable sensitivity. The quest to decode the universe's first light is accelerating, driven by a simple truth: to hear a quieter whisper, you must build a better ear. This next phase is not about a single telescope, but about vast arrays of them, creating a collective ear so powerful it can discern the faintest curl of polarization, the signature of spacetime's birth tremors. Leading this charge from the ground is the Simons Observatory. Perched high in the Atacama Desert of Chile, it is not one telescope but a suite of them. Its heart will be the Large Aperture Telescope, a massive 6-meter mirror, alongside an array of 3 smaller, wider field instruments. But the true revolution lies not in the mirrors alone, but in what they focus the light onto, arrays of superconducting detectors numbering in the tens of thousands. Each of these detectors is a tiny, exquisitely sensitive bolometer, chilled to a fraction of a degree above absolute zero. Where Planck had hundreds of detectors, the Simons Observatory will have tens of thousands, granting it the raw power to map the CMB's polarization with a precision and speed that dwarfs previous efforts. Its primary mission is the relentless hunt for the primordial B-mode signal, the curling pattern that could be the direct imprint of gravitational waves from inflation. Yet its power will also be turned like a forensic microscope onto the existing anomalies. With this new data, scientists will be able to perform the ultimate test. Do the axis of evil and the hemispherical asymmetry persist in this exquisitely detailed polarization map? Or do they finally fade into statistical noise, revealed as phantoms of a less precise era? The answer will either solidify these features as fundamental cosmic facts or finally lay them to rest. But the ambition stretches even further. On the horizon is CMB Stage 4 or CMB S4. This is not merely an observatory, it is a campaign. Envisioned as a network of multiple telescopes across the South Pole and the Atacama Desert, it aims to field 500,000 detectors. This colossal scale is necessary to achieve the ultimate sensitivity required to detect the faint inflationary B-mode signal, if it exists at the level predicted by many models. CMB S4 will also create a map of the CMB's temperature and polarization with such incredible resolution and freedom from foreground contamination that it could reveal entirely new classes of anomalies, features we cannot yet imagine because we have never had an instrument capable of seeing them. Yet the atmosphere itself, even in the driest deserts, presents a faint but persistent barrier. To reach the ultimate sensitivity, we must once again leave Earth behind. This is the goal of proposed space missions like LIGHT-BIRD, which stands for the Light Satellite for the study of B-mode polarization and inflation from dust. Its design philosophy is beautiful in its focus. It is a dedicated B-mode hunter, free from the shimmer and emission of Earth's atmosphere, and equipped with thousands of detectors cooled by a sophisticated space cryostat. LIGHT-BIRD would survey the entire sky for years, measuring the polarization across a wide range of frequencies with unmatched stability. Its mission is to measure the cosmic microwave background's polarization with such precision that it could confirm or rule out entire families of inflationary models, telling us not just if inflation happened, but how it happened. The data from these next-generation instruments will be more than just better pictures. They will be vast, multidimensional datasets, allowing scientists to separate the signal from the noise with a confidence we can only dream of today. We will see the polarized glow of galactic dust with such clarity that we can subtract it perfectly, leaving behind the pristine cosmic signal. We will measure the gravitational lensing of the CMB by the cosmic web in exquisite detail, using it to map the distribution of dark matter across cosmic time. These missions represent a leap into an era of precision cosmology where the questions shift from what the anomalies are to what they fundamentally mean. They are our best chance to transform the faint whispers in the ancient light into a clear message, one that could finally guide us to the laws that wrote the first page of our cosmic story. The universe's most profound data arrives not as a vision but as a torrent of numbers. For the satellites spinning in the silent dark, the cosmic microwave background is a relentless stream of voltage readings and timestamps, terabytes of time-ordered data documenting the precise moment a 13-billion-year-old photon struck a detector. This raw information is the ultimate truth, but it is utterly alien to human perception. To bridge that gap, to let us see the invisible, requires a magnificent act of translation. This is the art and science of cosmic cartography, where mathematics meets aesthetics to paint a portrait of creation. The most iconic image born from this process is the full sky map, often rendered in what is called a Mullwade projection. This oval-shaped projection is a cartographer's clever trick, a way to flatten the entire celestial sphere, every direction we can look, onto a two-dimensional surface with minimal distortion. Upon this canvas, the subtle temperature variations of the CMB are painted in color. Deep blues and purples might represent regions just a few millionths of a degree cooler than the average, while reds and yellows show the slightly warmer patches. This color scheme is not arbitrary. It is a carefully chosen legend, translating imperceptible physical differences into a spectrum our eyes can intuitively grasp. The resulting image is breathtaking, a cosmic mandala speckled with the hot and cold seeds of all future galaxies. But this beautiful map is not a single, definitive picture. It is the product of deliberate choices, each layer of processing designed to highlight a different feature of the hidden reality. The first and most critical step is subtraction. The dominant signal in the raw data is the dipole, that broad pattern caused purely by our solar system's motion through the cosmic sea. Scientists digitally remove this, essentially subtracting our own local velocity from the image, to reveal the universe as it would appear from a perfectly stationary vantage point. They also subtract the uniform average temperature, the monopole, leaving only the fluctuations. What remains is the true cosmic signal, the ancient whisper stripped of modern interference. Even then, visualization is an interpretive act. One color scheme might emphasize contrast, making the hot and cold spots appear stark and dramatic, perfect for public engagement. Another, more subtle palette might be used by researchers to visually scan for large-scale patterns or asymmetries. Specialized processing can be applied to highlight specific anomalies. To study the cold spot, scientists might generate a map that filters out all but the very largest angular scales, causing that vast, cool bruise to emerge clearly from the finer background texture. To examine the axis of evil, they might create a visualization that accentuates the alignment of the quadrupole and octupole moments, drawing those broad swaths across the map in a way that makes their curious orientation visually apparent. These images are far more than pretty pictures for magazine covers. They are the primary interface between the cold logic of the dataset and the pattern-seeking human mind. A cosmologist staring at a new visualization might notice a curious smudge or an unexpected gradient that purely statistical analysis had not yet flagged. That visual intuition can then guide the rigorous mathematics, prompting a new line of inquiry. It was in part by looking at early maps that scientists first sensed the large-scale asymmetry, a feeling that one half of the sky simply looked different before they proved it with numbers. The journey from raw data to profound insight is a story of computational prowess married to human creativity. It begins with the satellite spin, each point on the sky being measured thousands of times to build up signal and drown out noise. Sophisticated algorithms then clean the data, piece the scans together, and project the points onto the sphere of the sky. The final choice of color, scale, and projection is where science acknowledges its need for art. These visualizations perform an essential magic. They transform abstract data into a landscape we can explore. They allow every one of us to look directly into the face of the infant universe, to see with our own eyes the delicate imperfections from which we ourselves eventually arose. In this way, the map is both a tool of discovery and an object of wonder, a testament to our deep desire not just to know the cosmos, but to truly see it. Behind every pixel of that cosmic portrait lies a story of human collaboration on a planetary scale. The map of the infant universe is not the work of a lone genius in a secluded observatory. It is the crowning achievement of big science, a global endeavor involving thousands of scientists, engineers, and technicians from dozens of nations, all united by a single, profound question. Missions like the Planck satellite represent one of the largest and most complex cooperative efforts in the history of exploration. To grasp its scale, picture the mission's life cycle. It began with teams of physicists and engineers across Europe and North America, designing and building instruments of almost impossible sensitivity. Specialists in cryogenics worked to create cooling systems that could chill detectors to within a tenth of a degree of absolute zero in the harsh environment of space. Others perfected the delicate sunshield, a vast parasol that would keep the spacecraft in perpetual shadow, its instruments pointed forever into the cosmic cold. Once launched, the effort shifted to a different kind of craftsmanship. For years, the satellite silently spun and scanned, beaming back a river of raw data. On Earth, this data flowed into a distributed brain trust. Teams specializing in data pipelines wrote millions of lines of code to clean the time-ordered data, stitch together scans, and flag instrumental glitches. Another army of experts, the foreground modelers, dedicated their careers to understanding every possible contaminant, from the spiral arms of the Milky Way to the faint radio hum of distant quasars, creating the digital brushes that would clean the canvas. Then came the theoretical interpreters, the cosmologists who took the pristine map and interrogated it with equations, translating its patterns into the language of universal constants and cosmic ingredients. This division of labor is a hallmark of modern cosmology. It is a culture built on a careful, often delicate balance. There is intense competition to be first to a discovery, to ask the most insightful question of the data. Yet this exists alongside a foundational commitment to open data sharing. After a proprietary period, the entire Planck dataset was released to the world, enabling researchers everywhere, from major institutions to small colleges, to scour the maps for new clues. This openness accelerates discovery, inviting fresh eyes and novel techniques to examine our shared cosmic heritage. The result is a scientific tapestry woven from threads of individual brilliance and collective purpose. When we gaze at that full sky map with its intricate patterns, we are not just looking at the afterglow of the Big Bang. We are witnessing a monument to human curiosity and perseverance. It is a map charted by the combined intellect of our species, a reminder that to decode the grandest secrets of the cosmos, we must first learn to work together here on our fragile, pale blue dot. These quiet imperfections in the ancient light ask us something far deeper than physics. They challenge a bedrock idea that has shaped our view of the cosmos for centuries, the Copernican principle. This is not just an astronomical rule, it is a philosophical stance, a declaration that we do not occupy a privileged or central position in the universe. Everywhere should look roughly the same, yet the axis of evil, that eerie alignment that seems to point toward our own solar system, whispers a troubling counterpoint. If it is real and not a trick of the data, then on the largest scales we can observe, the universe does have a subtle grain, a direction, and by a staggering coincidence, that direction is aligned with us. This does not mean we are at the center of a cosmic bullseye, but it might suggest our local patch of space-time is somehow linked to the universe's deepest architecture. Are we seeing a fossil of a pre-existing condition, a spine in the cosmos that just happens to run through our neighborhood? The very question forces a profound shift in perspective. For so long, we have defined scientific progress as moving away from a self-centered view of reality. Now, the oldest map we have seems to quietly, persistently, include our address. This leads to an even more fundamental question about the nature of discovery itself. When is a strange pattern a genuine clue, and when is it just a trick of the light? Throughout the history of science, anomalies have been the engines of revolution. The slight wobble in Mercury's orbit hinted at the curvature of spacetime described by general relativity. The unexpected stability of light speed led to Einstein's theory of special relativity. In each case, a stubborn, unexplained detail became the key to a larger truth. The anomalies in the cosmic microwave background now sit in that precarious, exhilarating space. They have survived years of scrutiny and rigorous data cleaning. Their statistical significance, while not definitive, is too persistent to ignore. They could be the first faint cracks in our standard model of cosmology, hints of a richer physics operating at energies we can never hope to recreate in a laboratory. Perhaps they point to a multiverse, a finite cosmos, or a more complex beginning than simple inflation. To dismiss them outright would be to ignore history's lesson that the universe often speaks most clearly through its whispers. Yet the scientific mind must also hold a deep respect for randomness. With a dataset as vast as the CMB map, containing millions of pixels, some patterns will inevitably emerge by pure chance. Our brains are wired to find meaning in randomness, to see faces in clouds and constellations in stars. The crucial, disciplined work is to determine whether the face in the cloud is actually a mountain. This tension is the very heart of the scientific process. It requires a beautiful balance of two seemingly opposite traits: radical open-mindedness to new possibilities and ruthless skepticism toward one's own desires. The cosmologists studying these maps must be both dreamers and detectives, willing to chase a faint clue across the universe while simultaneously building a case against it, trying to prove it wrong. This is not a flaw in the process, it is its greatest strength. It is how we guard against seeing only what we wish to see. In this way, the cosmic microwave background becomes more than a snapshot of the past. It becomes a mirror. When we stare into its speckled depths, we are also staring at our own assumptions about reality. We assume uniformity. We assume isotropy. We assume the laws of physics are the same everywhere and at all times. The map generally confirms these assumptions with spectacular success, which is why the few places where it hesitates are so captivating. They reflect back to us the limits of our current understanding. Engaging with these patterns is therefore an exercise in both cosmic humility and immense intellectual ambition. Humility, because we must accept that our most elegant theories might be incomplete sketches of a grander masterpiece. Ambition, because we dare to believe that by patiently decoding this ancient light, we can correct the sketch, moving closer to a true portrait of reality. The map does not give us answers. It simply holds up a silent, question-marked face to the universe, and by extension to ourselves. What we choose to see in it next will define not just the future of cosmology, but our evolving story of what it means to be a conscious observer in a vast and mysterious cosmos. The thrill of cosmic mysteries can sometimes blur the line between what the data says and what we might wish it meant. With features as evocative as the axis of evil or a cold spot spanning a billion light-years, it is natural for speculation to run wild, often outpacing the cautious conclusions of science. One of the most persistent misconceptions is that the axis of evil is a literal, physical axis around which the universe rotates, or even a sign of intentional design. In reality, it is a statistical description of an alignment in the data, a subtle preference in the orientation of the very largest patterns. The name itself, while memorable, is a piece of scientific dark humor highlighting the problem the anomaly poses to standard theory, not a declaration of cosmic malice or divinity. Cosmologists are not suggesting the universe has a giant pole running through it. They are reporting that the map, against all expectation, is not perfectly random. The cause remains unknown, and the leading explanations are physical, from anisotropic inflation to complex foreground effects we have yet to fully model. It is a puzzle, not a prophecy. Similarly, the cold spot is frequently described in popular articles as a gigantic, empty void, a cosmic hole in space. This framing, while visually striking, is misleading. The supervoid explanation is just one hypothesis, and as we have seen, the observed underdensity of galaxies in that direction does not match the immense scale required to produce the chilling effect through standard physics. Calling it a universe-sized void implies we have found a staggering nothingness, when in truth, we have found a profound mismatch between observation and prediction. The spot is cold, but the space it appears to occupy is not nearly as empty as the simplest void theory would demand. This gap between the model and the measurement is the real mystery, pointing toward either a colossal statistical fluke or a more exotic cause, like a texture in spacetime or a multiverse collision. The science is in the tension between the map and our models, not in a simple label. This leads to another crucial clarification: the multiverse. In scientific cosmology, the multiverse is not a single idea, but a set of theoretical consequences arising from well-established frameworks like eternal inflation or string theory. It is a prediction that emerges from the mathematics, not a philosophical preference. When researchers suggest the cold spot could be a bruise from a bubble collision, they are working from specific, calculable models that generate testable signatures. This is a world apart from purely philosophical notions of infinite parallel realities for every choice we make. The scientific multiverse hypothesis is often frustratingly untestable, but in rare cases, like a potential imprint on the CMB, it offers a narrow window for empirical scrutiny. Distinguishing between these concepts is vital. It separates speculative but rigorous theoretical work from boundless, evidence-free imagination. By untangling these misconceptions, we do more than correct facts. We reveal the true nature of the scientific endeavor. Cosmologists are not mystics reading celestial tea leaves. They are detectives working with a fragile, ancient piece of evidence. Their challenge is to interpret its faint marks without letting hope or preconception write the story for them. Every anomaly is met with a barrage of statistical tests and attempts to explain it away with known physics, because the most conservative explanation is usually the right one. This disciplined skepticism, this constant navigation between the excitement of a potential breakthrough and the rigor of demanding proof, is what protects the field from fantasy. It empowers us all to engage with these breathtaking discoveries critically, to appreciate not just the strange features on the map, but the careful, nuanced, and profoundly human work of those who strive to read it. The blueprint for the cosmos was set in stone before the first star ever ignited. Those faint hot and cold spots on the ancient map are not merely a fossil record. They are the active seeds from which every galaxy, cluster, and filament in the observable universe would eventually grow. This is the profound connection between the universe's first light and its present-day grandeur, a causal chain written by the relentless force of gravity over billions of years. Think of a slightly warmer region on that cosmic microwave background map. That tiny patch, just a few millionths of a degree hotter than its surroundings, represented a minuscule overdensity, a place where the primordial soup of matter and radiation was ever so slightly thicker. In the aftermath of the universe becoming transparent, gravity began its slow, patient work. That extra bit of mass exerted a slightly stronger gravitational pull, drawing in more material from the surrounding regions. Over millions of years, then hundreds of millions, this snowball effect accelerated. Dark matter, invisible and pervasive, formed the gravitational skeleton first, creating deep wells of potential. Ordinary matter, the atoms that would become stars and planets, flowed along these invisible contours, cooling and condensing within them. What began as a microscopic quantum fluctuation, stretched to a scale of hundreds of thousands of light years by inflation, became the nursery for a future galaxy cluster. But this is not just a theoretical story. We can witness this epic transformation unfold through the power of supercomputer simulations. Cosmologists feed the precise statistical properties of the cosmic microwave background, the exact spectrum of those hot and cold spots, into vast virtual universes. They program in the known laws of physics with gravity as the lead actor and then press play. The simulations run for the equivalent of 13.8 billion years in a matter of weeks. Watching the output is like seeing a time lapse of the cosmos itself. The initially smooth, speckled distribution of matter begins to clump. Tendrils of dark matter reach out and connect, forming a vast, intricate cosmic web. The densest knots at the intersections of filaments grow into brilliant hubs of light, representing galaxy clusters containing thousands of galaxies. The simulations produce a universe that looks, in its statistical architecture, unmistakably like our own. This virtual prediction is then compared to the real universe mapped by ambitious sky surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument, or DESI. These projects have painstakingly measured the positions and distances of millions of galaxies, creating three-dimensional charts of the cosmic web on a scale never before seen. The question is profound: does the pattern of galaxies we see today match the pattern predicted from the infant universe's imperfections? The answer is a resounding yes. The statistical distribution of galaxies, the clustering strength, the sizes of voids and filaments, all align with extraordinary precision with the predictions extrapolated from the cosmic microwave background's power spectrum. It is a match made over 13 billion years. This connection is one of the strongest validations of our entire cosmic narrative. It closes the loop. We have the initial conditions from the cosmic microwave background, the physical laws of gravity and dynamics, and the final observed structure. All three pieces of the puzzle fit together seamlessly. This turns the ancient map from a historical artifact into a predictive engine. By reading the subtle patterns in that first light, cosmologists can not only explain the past but forecast the large-scale distribution of matter in the universe. They can predict with remarkable accuracy how the cosmic web should look on scales far larger than any survey can currently map. The cosmic microwave background is therefore more than a baby picture. It is the founding document, the constitutional charter for the universe's entire architectural project. Every glittering city of galaxies we see in the deep field images from the Hubble and Webb telescopes owes its existence and its location to a specific, faint whisper of warmth on that ancient cosmic map. The universe's first photograph comes with a fundamental resolution limit. For all its staggering detail, the cosmic microwave background is not a perfect, infinite source of data. It is a single, unique snapshot of a one-time event, and that fact alone places a profound ceiling on what we can ever learn from it. This ceiling is known as cosmic variance, and it is a concept born from a simple, humbling truth: we only have one universe to observe. Think of it this way: if you wanted to understand the average height of humans, you would measure many individuals. Your statistical uncertainty would shrink with each new person you added to your sample. But what if your entire species consisted of just one person? You could measure that person with exquisite precision, but you would have no way of knowing if they were typical or a bizarre outlier. Your sample size is 1. This is our predicament with the cosmos. The very largest patterns in the CMB, like the faint quadrupole and octupole, are each a single sample. We see one quadrupole pattern stretched across our entire sky. Is its surprising faintness a profound clue about the shape of the universe? Or is it simply the random card our universe happened to draw from the quantum deck? Cosmic variance tells us we may never know for certain. It is a statistical noise floor, a built-in uncertainty that no future telescope, no matter how powerful, can ever overcome. Some questions about the grandest scales of reality may be eternally unanswerable, their clues forever blurred by the simple fact that we live inside the only experiment we can measure. Our vision is blurred at the other end of the scale as well, in the realm of the extremely small. As we examine finer and finer details on the CMB map, the sharp features gradually fade into a smooth haze. This is called the damping tail. To understand why, return to the moment of last scattering. The universe did not become transparent instantaneously like a curtain being ripped away. It was a process. For a final period, photons were still bumping into electrons, scattering and rescattering as they struggled to escape the thinning plasma. This was a cosmic diffusion, a blurring effect. Imagine a brilliant, intricate pattern painted on a pane of glass, and then a thin fog rolls in, just for a moment before clearing. The largest features of the painting remain sharp, but the finest details, the most delicate brushstrokes, are softened and lost. The damping tail is that fog. It erases the tiniest temperature variations, the quantum whispers on the smallest scales, because those photons had more time to jumble their message before finally breaking free. This sets another hard limit. It means the cosmic microwave background will never reveal the universe's most minute initial fluctuations. That information was scrambled in the final moments of the primordial fog and is gone forever. Adding to this blur is the fact that the last scattering surface is not a razor-thin sheet. It has a thickness of roughly 115,000 light-years. We are not looking at a single instant, but at a composite image spanning thousands of years of cosmic evolution. Photons from the front of this shell left slightly earlier than photons from the back, and they come from regions that had slightly different densities and temperatures. This thickness acts like a lens slightly out of focus, blending together features that are close together on the sky. It is why the smallest spots on the map have a characteristic smeared appearance, a fundamental limit to the sharpness of our baby picture. Acknowledging these limits is not an admission of failure, it is an act of scientific maturity. It defines the playing field. cosmic variance tells us which mysteries, like the true nature of the largest scale anomalies, might remain forever in the realm of compelling hints. The damping tail and finite thickness show us where the map genuinely ends, where the data runs out. They frame our knowledge, showing us the breathtaking expanse of what we can learn from this ancient light, while also drawing a definitive border around it. Within that border, we have extracted a universe of understanding. Beyond it, we must accept that some chapters of the cosmic origin story were written in ink that has permanently faded, leaving us to wonder at the lost text from the very first page. The story of these cosmic whispers is a chronicle of our growing vision. It begins not with certainty, but with a faint, intriguing blur in the first grainy portrait of the infant universe. In the 1990s, NASA Cosmic Background Explorer (COBE) delivered a revelation. The cosmic microwave background was not perfectly smooth. Its map, though low in resolution, showed the first undeniable speckles, the primordial seeds of structure. Yet within that triumph, a quiet curiosity lingered. The very broadest patterns in the COBE data, the largest swaths of warmth and coolness, seemed curiously faint. It was a whisper within a whisper, a hint that the universe's largest canvas might be quieter than anyone had predicted. This was the first suggestion of the low quadrupole, a puzzle that would only deepen with time. A decade later, the narrative sharpened dramatically with the Wilkinson Microwave Anisotropy Probe, WMAP. Its maps were far clearer, revealing the acoustic peaks with stunning definition and solidifying the standard model of cosmology. But with greater clarity came greater mystery. The subtle quirks noted by COBE did not vanish, they crystallized. The lack of large-scale correlation became a firm statistical feature. More startlingly, researchers analyzing the WMAP data identified a strange coherence in the orientation of these largest patterns, a curious alignment that would soon earn its dramatic nickname, the Axis of Evil. The puzzles were no longer vague hints. They were specific, measurable features etched into the most precise map of creation ever made. The plot thickened further with the arrival of the European Space Agency's Planck satellite in the 2010s. Planck was a quantum leap in sensitivity. It observed the sky across 9 different frequencies, allowing for an unprecedented cleansing of foreground contamination from our own galaxy. If the anomalies were mere smudges on the lens, Planck would wipe them away. Instead, it refined them. The axis of evil persisted. The hemispherical asymmetry, the lopsided power between two halves of the sky, emerged with new clarity from Planck's multi-frequency analysis. The cold spot remained cold and enigmatic. What changed was not the presence of these features, but our understanding of their stubborn reality. With each new generation of data, the possibility that they were simple artifacts or noise grew smaller and smaller. Their persistence across independent missions, built with different instruments and analyzed by different teams, transformed them from curious glitches into persistent cosmic questions. This historical arc reveals science not as a series of sudden eureka moments, but as a slow, meticulous conversation with reality. An anomaly is not a revolution, it is an invitation. It invites better instruments like Planck to see if the signal remains. It invites more sophisticated analysis to rule out every possible mundane explanation. And finally, it invites bold new ideas, theories of anisotropic inflation or cosmic topology, that might explain why the universe's first light tells this particular story. Some features, like the low quadrupole, have been with us for 30 years, a quiet background hum in our cosmological model that refuses to be explained away. Others, like the detailed nature of the cold spot, have seen their leading explanations shift from a simple supervoid to more exotic possibilities, as follow-up observations failed to match the initial theory. This is the process in action, a cycle of discovery, interpretation, and reinterpretation. The narrative is far from over. the baton is now passing to a new generation of observatories like the Simons Observatory and the proposed CMB-S4 project. Their mission is to listen with ears 10 times more sensitive than Planck's, to map the polarization of the ancient light in exquisite detail. They will ask the next chapter's critical questions. Do these anomalies imprint themselves on the polarization map as well, cementing their status as fundamental features of reality? Or, in the glare of this new light, will they finally dissolve, revealed as phantoms of a less precise age? The history of the cosmic microwave background teaches us that the universe guards its deepest secrets closely, revealing them not in shouts, but in whispers that grow clearer only as we learn patiently how to listen. To judge whether our universe is ordinary or strange, we must first create 1,000,000 copies of it. This is the monumental task of computational cosmology, where the world's most powerful supercomputers are dedicated to running the ultimate cosmic experiment in a box of silicon. These are not simple animations, they are precise, mathematical universes born from equations, evolving under the strict laws of physics to produce their own simulated cosmic microwave background. The process begins with a single, profound assumption that the initial conditions of the cosmos were set by quantum fluctuations during inflation. The computer starts with a three-dimensional grid representing a cubic volume of the early universe. Onto this grid, it imposes a random field of tiny density variations, a digital seed of Gaussian noise whose statistical properties exactly match the predictions of the inflationary model. This is the digital equivalent of the primordial quantum jitter. Then, with this seed in place, the simulation presses play. It must solve the complex equations of general relativity and fluid dynamics for a plasma of particles and radiation, tracking how each point on the grid evolves over cosmic time. The calculation marches forward from a fraction of a second after the Big Bang, through the era of nucleosynthesis where light elements formed, and into the 300,000-year journey toward transparency. The most critical moment is recombination. The simulation must calculate for every point in this virtual sky the precise moment when atoms form and photons decouple. It models the last scattering of those photons, tracing their paths as they finally stream free. The result is a two-dimensional map, a fully simulated cosmic microwave background sky as it would be seen by a hypothetical observer inside that virtual universe. But one simulated sky is meaningless. The power of this approach lies in repetition. Scientists run this entire process not once but thousands upon thousands of times. Each run starts with a different random seed, a different roll of the quantum dice, generating a completely unique universe with its own pattern of hot and cold spots. This massive ensemble creates a statistical library of possible cosmic outcomes. From this library, we can answer fundamental questions. What is the average strength of the quadrupole moment across 10,000 random universes? How often does a cold spot as large and as cold as ours appear purely by chance? What is the natural range of hemispherical asymmetry in a statistically isotropic cosmos? This library defines the cosmic normal. It tells us what the standard model of cosmology actually predicts, not in a single perfect instance, but across the full spectrum of random chance. Our one observed universe is then compared against this vast crowd of its simulated siblings. When we say an anomaly has a 3 sigma significance, what we are really saying is that in our library of 10,000 simulated skies, only about 30 of them showed a feature as extreme as the one we see in our real data. This brute force computational approach transforms abstract statistics into a tangible, visual comparison. It grounds our wildest cosmic patterns in rigorous numerical reality. Without these simulations, every strange feature on the CMB map would be a subject of pure speculation. With them, we can assign precise probabilities, separating the likely flukes from the genuine cosmic mysteries. The supercomputers running these codes with names like Summit and Frontier perform quintillions of calculations per second, yet a single high-resolution cosmic simulation can still take months. They are the silent engines of modern cosmology, tirelessly generating the multiverse of possibilities against which our one precious reality is measured. The universe's first light is a Rosetta Stone for more than just cosmology. Its faint patterns speak a language that resonates across the entire landscape of modern science, from the tiniest particles to the most abstract theories of reality. This is where the cosmic microwave background becomes an interdisciplinary crossroads, a single dataset that demands expertise from fields seemingly worlds apart. Perhaps the most direct conversation is with particle physics. The CMB provides a pristine laboratory from a time when the universe was a searing, high-energy collider, far beyond anything we can build on Earth. Its precise measurements act as a strict referee for theories about the universe's most elusive components. For instance, the exact shape of the acoustic peaks constrains the number of neutrino species and even their total mass. These ghostly particles, streaming through the universe by the trillions, left a subtle imprint on how matter clumped in the early cosmos, and the CMB map captures that imprint. Similarly, the inventory of dark matter revealed by the CMB's power spectrum rules out entire classes of hypothetical particles, guiding physicists as they design experiments to hunt for these mysterious entities in underground labs and space-based observatories. The map is a boundary condition telling particle physicists what their models must ultimately explain. The connection stretches even further into the realm of quantum gravity and string theory. The first fleeting moments after the Big Bang, probed indirectly by the CMB's largest scale patterns, are the only empirical window we have into physics at the Planck scale, where gravity and quantum mechanics are thought to unite. While we cannot see that era directly, its aftermath, the statistical properties of those initial fluctuations, holds clues. Does the pattern of hot and cold spots show any sign of the discrete, granular nature of spacetime predicted by some theories of quantum gravity? Could the anomalies hint at extra dimensions, as suggested by certain string theory models? The CMB data provides a crucial reality check for these extraordinarily abstract ideas, tethering them to observable evidence. Beyond fundamental physics, the analysis of this ancient light has sparked a revolution in data science itself. The datasets from missions like Planck are not simple pictures. They are high-dimensional, petabyte-scale torrents of information, contaminated by complex, overlapping foregrounds. Making sense of it requires cutting-edge tools from information theory and machine learning. Scientists employ sophisticated algorithms, like convolutional neural networks, to sift through the noise, separating the cosmic signal from galactic dust with a precision that traditional statistics could never achieve. Other techniques from compressive sensing help reconstruct the full sky map from incomplete scans. Much like a medical MRI builds an image of the body from scattered measurements. The quest to understand the cosmos is now deeply intertwined with the quest to manage and interpret colossal amounts of data, pushing the boundaries of computer science in the process. This beautiful synthesis reveals a profound truth about our pursuit of knowledge. Understanding the universe's first light is not a task for astronomers alone. It requires the particle physicist to model the early plasma, the theorist to conceive of the inflationary landscape, the data scientist to clean the signal, and the computer engineer to build the detectors that capture it. Cosmology has become a unifying endeavor, a grand collaborative project that draws from every corner of human ingenuity. In decoding the map of creation, we are not just learning about the origin of galaxies. We are witnessing the power of a connected scientific mind, proving that the deepest mysteries of the cosmos can only be solved when we bring all of our tools to the table. The map of creation is not locked away in academic journals. Its story is being told in darkened domes and on glowing screens, transforming abstract data into shared wonder. One of the most powerful ways to experience the cosmic microwave background is not through a scientific paper, but by looking up inside a planetarium. Here, advanced digital projectors can wrap the entire full sky map around an audience, immersing them in the speckled panorama of the infant universe. Viewers do not just see a flat image, they are surrounded by it, floating inside the ancient light. Narrators guide them through the warm and cold spots, explaining how these subtle imperfections are the blueprints for the very dome above their heads, connecting the dots on a cosmic scale to the stars in the night sky they see when they leave the theater. This visceral, embodied experience makes the scale and significance of the CMB tangible in a way graphs and numbers alone never could. For those exploring from home, a wealth of interactive online tools now puts this cosmic data at their fingertips. Websites and applications allow anyone to zoom, pan, and filter the Planck satellite maps, toggling between different frequency bands to see how scientists peel away the foreground glow of our galaxy. Users can even adjust simulated parameters like the amount of dark matter or dark energy, and watch in real time how the predicted pattern of acoustic peaks shifts on a graph. This transforms the public from passive observers into active explorers, demystifying the process of cosmology itself. The central challenge in all this outreach is translating an almost imperceptible signal into human experience. How do you convey the meaning of a map where the most dramatic feature is a region just a few millionths of a degree warmer than its neighbor? Educators have found tremendous success in the analogy of sound. The universe before transparency was not silent, it was ringing. By converting the temperature fluctuations into actual audio frequencies, the CMB can be heard as a deep, resonant chord that slowly descends into a lower hum. This is not an artistic interpretation, it is a direct sonification of the data. It allows people to hear the acoustic oscillations, to perceive the peaks in the power spectrum as distinct notes in a cosmic symphony. This framing of frozen music, a snapshot of the universe's first vibrations, makes the abstract beautifully concrete. It connects the science to a universal human experience of rhythm and harmony. By investing in these creative forms of communication, scientists do more than share exciting results. They build a vital bridge of understanding, a public that grasps the profound journey from quantum whisper to galactic city is a public that values fundamental discovery. This appreciation translates into support for the ambitious and often costly missions that push the frontier forward. From ground-based telescopes in remote deserts to future satellites that will listen for the curl of primordial gravitational waves. Every planetarium show, every interactive website, every sonification of the ancient sky is an invitation. It is an offer to join the greatest detective story ever told, to look at a map of faint imperfections and see within it the spectacular origin of everything we know. There is a profound beauty in this ancient blueprint, a minimalist art painted not by a hand but by the fundamental laws of reality. The cosmic microwave background map, when stripped of its scientific labels and color-coded legends, stands as a stark and mesmerizing aesthetic object. Its mottled texture of warm and cool spots, spread across the oval projection of the entire sky, resembles a celestial pointillist painting or a weathered stone etched by eons. This is not a representation of something else, it is the thing itself, the direct imprint of the universe's first visible moment. The beauty we perceive in it is deeply tied to its origin, a pattern born from quantum randomness stretched to a scale beyond human comprehension. Each speck is a monument to a fluctuation so small it defies description, now frozen as a feature spanning millions of light years. This transformation, from quantum whisper to cosmic landscape, evokes a visceral sense of deep time and unimaginable space, connecting us to a narrative that begins long before our own story. We are drawn to this image for the same reasons we are drawn to standing beneath a star-filled sky or contemplating the ocean's horizon. It speaks to fundamental human themes of origin, of searching for patterns in the chaos, and of confronting a mystery that is both vast and intimately connected to our own existence. The map's aesthetic power lies in its sublime coherence. It is a complete picture that is also an unsolved riddle. Recognizing this dimension is crucial, for it reminds us that the scientific drive to decode the cosmos is not a cold, purely analytical exercise. It is equally fueled by a sense of wonder, by the same awe that inspired our earliest myths and stories. We seek to understand this map not just to fill textbooks, but to satisfy a deep-seated desire to see our own place within a grand, beautiful, and coherent narrative. The quiet, speckled face of the infant universe reflects back to us a story of emergence, where everything we know and are began within these subtle variations. In contemplating its stark beauty, we engage in an act that is both scientific and profoundly human, connecting the logic of physics to the poetry of our place in time. The most thrilling cosmic whispers can sometimes be echoes from our own instruments. Before we can accept that the universe's blueprint contains true anomalies, we must perform the most rigorous audit possible, scrutinizing every step from the satellite's sensor to the final colored map. A cornerstone of scientific integrity is the principle of parsimony, often called Occam's razor, which suggests the simplest explanation, the one requiring the fewest new assumptions, is often correct. In the context of the cosmic microwave background, the simplest explanation for a strange feature is not a multiverse collision or a pre-Big Bang cosmos, but a subtle error in our own analysis. This critical perspective is not skepticism for its own sake. It is the essential guardrail that keeps discovery honest. Teams of researchers have dedicated years to this forensic work, asking if the data itself might be misleading us. Take the axis of evil, that eerie alignment with our solar system's plane. Could it be a ghost in our own machine? One compelling line of inquiry focuses on something called kinematic dipole subtraction. We know our solar system is moving through the cosmic microwave background, creating a massive temperature dipole, a hot spot ahead and a cold spot behind. To see the pristine ancient sky, we digitally subtract this dipole from the map. But what if our measurement of our own motion, or the model for subtracting it, is imperfect by just a tiny amount? Even a minuscule residual from this subtraction, a leftover smudge aligned with our motion, could potentially imprint a spurious large-scale pattern on the cleaned map. Some studies have argued that when different methods for handling this local contamination are applied, the statistical significance of the axis of evil diminishes, sometimes falling into the realm of plausible random chance. Similarly, the profound cold spot faces intense statistical scrutiny. Its discovery was by necessity a form of a posteriori analysis. Scientists did not predict a specific billion-light-year wide cold region at a particular set of coordinates. Instead, they looked at the completed map and asked, what is the coldest, most unusual patch we can find? When you search a dataset containing millions of pixels for the most extreme outlier, you will always find one. The critical question is, how extreme is it compared to what you would expect from pure randomness? Several research groups have applied different statistical techniques to assess the cold spot's significance. Some methods which account for the fact that we went looking for the most unusual feature after the fact suggest its probability of being a random fluctuation might be as high as 1 in 50 rather than 1 in 1,000. This does not make it ordinary, but it does place it in a category where a colossal but natural statistical fluke remains a plausible, if astonishing, explanation. The process of foreground subtraction itself is another vast source of potential systematic error. Our galaxy's complex emission is modeled and removed using data from multiple frequencies. But what if our models of interstellar dust are slightly wrong? What if there is a faint, diffuse component of galactic emission we have not yet characterized, one that has a pattern mimicking a large-scale asymmetry? Some papers propose that an incomplete modeling of this foreground, particularly something called anomalous microwave emission, could create artifacts that look like the hemispherical power asymmetry or affect the largest scale correlations. The scientists working on these missions are the first to acknowledge these possibilities. The Planck collaboration's own publications dedicate hundreds of pages to characterizing systematic errors, testing the data with countless alternative analysis pipelines. This work is slow, meticulous, and unglamorous, but it is the bedrock of trust. It represents a collective commitment to doubt, a willingness to spend years trying to prove a beautiful anomaly wrong before declaring it a window to new physics. This balanced view is not a dismissal of wonder, it is its necessary counterpart. It ensures that if a feature like the axis of evil or the cold spot does survive this relentless gauntlet of tests, its message will be all the more powerful. The truth in cosmology is not found by chasing the most exciting story first, but by patiently and sometimes painfully eliminating every other possible story. It is a discipline of humility, reminding us that the universe is under no obligation to be strange, and that our own capacity for error is often the most complex mystery we must solve. The quest to map the universe's first light is a monumental investment of human resources. We must ask a difficult but necessary question: is it ethical to spend billions on satellites and telescopes when our own world faces so many pressing challenges? The price tag for a mission like the Planck satellite was well over 700 million euros. Ground-based observatories like the Simons Observatory represent investments of hundreds of millions of dollars. These sums could build hospitals, fund schools, or address environmental crises. This tension is real, and it deserves thoughtful consideration. The justification for big science rests on several pillars, beginning with the intrinsic value of fundamental knowledge. Understanding our cosmic origin is a profound human endeavor, a chapter in the story we tell about our place in existence. This pursuit of meaning, of answering the deepest questions we can ask, is a good in itself, enriching our culture and expanding the horizons of human thought. It is an investment not in concrete, but in consciousness. Secondly, the technological challenge of building these instruments pushes engineering to its absolute limits, creating innovations that ripple through society. The need to process the CMB's colossal datasets has driven advances in computing and data compression. The superconducting detectors developed for these telescopes have potential applications in medical imaging and quantum computing. The precision required to map millionths of a degree in space fosters breakthroughs in materials science and cryogenics. We cannot predict which spin-off will next transform our daily lives, but history shows that reaching for the stars often plants seeds that bloom on Earth. Finally, there is the powerful, intangible benefit of a shared story. A map of the infant universe, a picture that belongs to no single nation or culture, has a unique unifying power. It reminds us viscerally that we all inhabit the same fragile planet under the same ancient sky. In a world often divided, this common cosmic heritage can be a source of perspective and shared wonder, fostering a sense of global citizenship. The ethics of this pursuit are further upheld by a foundational principle in modern cosmology: open data. After a proprietary period where the mission teams perform their initial analysis, every single byte of data from missions like Planck and WMAP is released to the public, freely accessible to anyone in the world with an internet connection. This is a deliberate ethical commitment. It declares that the universe's story is a common treasure. It democratizes discovery, allowing a student in a modest university lab or an independent researcher to scour the same data as the largest institutions, to ask their own questions and potentially make their own breakthroughs. This transparency builds global trust in the scientific process and ensures that the monumental cost of these projects yields a dividend of knowledge for all of humanity, not just for a privileged few. The investment in cosmic cartography, therefore, is weighed not just in currency but in legacy. It balances the urgent needs of today against the timeless human need to understand, to explore, and to ensure that the grand narrative of the cosmos is authored and owned by everyone. That ancient map is more than a scientific dataset, it is a mirror. When we look at those faint speckles, the hot and cold seeds of galaxies, we are not just seeing the universe's beginning, we are seeing our own. Every atom in your body, the calcium in your bones, the iron in your blood, the oxygen in your lungs, was forged in the heart of a star that lived and died long before our sun was born. And those stars themselves coalesced from clouds of gas that were drawn together by gravity, pulled toward the very density imperfections frozen into that cosmic microwave background. The line of causality is breathtakingly direct. The quantum jitter of an inflationary field, magnified to a cosmic scale, became a warm patch on this map. That warm patch gathered dark matter and then gas, which collapsed into the first generations of stars. Those stars, in their violent lives and explosive deaths, scattered heavy elements across space, which eventually became part of a molecular cloud, a new star we call the Sun, and a rocky planet. You are literally made of stardust, and the blueprint for that stardust is written in the light from the universe's first 380,000 years. To study this map is therefore an act of profound self-discovery, a way to trace our lineage not just through biological evolution, but through cosmic evolution, back to the very first structures that emerged from the formless fire of the Big Bang. It is also the closest we will ever come to time travel. The light hitting the detectors of the Planck satellite had been traveling for over 13 billion years, untouched since the moment it was set free. When you look at a visualization of that data, you are not looking at an artist's impression or a simulation. You are witnessing an event that happened before the Earth existed, before the Milky Way spiraled into shape. You are seeing the universe become transparent for the very first time, watching as the fog lifts on reality itself. This perspective is both humbling and empowering. It places our fleeting human story within an epic narrative spanning billions of years, reminding us of our recent and fragile arrival on a pale blue dot adrift in a vast cosmic ocean. Yet it also celebrates a staggering triumph of the human mind, that we, conscious creatures arising from this process, have developed the language of mathematics and the tools of technology to capture this whisper, to clean it of noise, and to learn to read its story, is a testament to our insatiable curiosity. We have taken the universe's first photograph and decoded its hidden text. In doing so, we have connected our moment of awareness here and now directly to the moment of creation there and then. The map does not tell us we are at the center of everything. It tells us something far more beautiful, that we are woven into the fabric of everything, from the first quantum fluctuation to the present thought. This connection is the ultimate gift of the cosmic microwave background, transforming a scientific achievement into a deeply personal reflection on origin, place, and the extraordinary capacity to understand. The map is complete, but its story is not yet finished. These quiet anomalies, these faint smudges on the blueprint of creation, have not been explained away. They stand as the great unanswered questions of cosmology, the frontier where our knowledge meets the unknown. Is the axis of evil a genuine feature of the cosmos, a fossil pointing to a direction imprinted at the beginning, or is it the final, most stubborn ghost in our data processing machine? If it is real, what physical process could possibly align the universe's largest patterns with the humble plane of our own solar system? the answer could rewrite our understanding of cosmic inflation or hint at a fundamental anisotropy woven into spacetime itself. Then there is the profound chill of the cold spot. Is it a statistical fluke of almost unbelievable scale, a supervoid we have somehow failed to fully map, or is it something far more exotic, a scar from a collision with another universe in a frothing multiverse? Each possibility opens a door to a radically different vision of reality. The hemispherical asymmetry and the missing large-scale correlations whisper similarly profound questions. Do they point to a more complex version of cosmic inflation, perhaps driven by multiple interacting fields? Or could they be evidence that the universe is not infinite but finite and wrapped in a complex unseen shape, a cosmic hall of mirrors where the largest waves simply cannot fit? And what of the most anticipated signal of all, the primordial B-mode polarization, the curling signature of gravitational waves from inflation's first shudder? Will we ever detect it? If we do, it will tell us directly about the energy scale of the universe's explosive birth, guiding us toward a grand unified theory of physics. If we do not, it may force us to reconsider the entire inflationary paradigm, sending theorists back to the drawing board. These are not failures of our science. They are its engines. Every unexplained feature on that ancient map is a destination for the next generation of telescopes, a puzzle for the next theoretical breakthrough. They remind us that the universe is under no obligation to be simple or to conform to our most elegant models. The pursuit of these answers is what drives missions like the Simons Observatory and dreams of future satellites. It fuels late-night discussions in labs and the scribbling of equations on whiteboards around the world. These questions are more than technical challenges. They are the latest chapter in humanity's oldest and most persistent quest to understand where we came from, what the universe is ultimately made of, and what our place is within this grand, mysterious, and beautiful story. The map of the first light is not a final answer. It is an invitation to keep looking. Our journey through the secret patterns of the cosmic microwave background reveals a universe that is both astonishingly orderly and intriguingly quirky. This ancient light serves as our most precise cosmological tool, confirming the grand narrative of the Big Bang and measuring the cosmos's contents with breathtaking accuracy. Yet, the very same map that validates our standard model also presents us with stubborn anomalies that defy easy explanation. These are not mere glitches or digital noise. The axis of evil, that eerie alignment pointing toward our own cosmic neighborhood, and the profound chill of the billion-light-year-wide cold spot are potential signposts to physics beyond our current models. They whisper of possibilities that stretch the imagination, from a multiverse of colliding bubble realities to echoes from a time before the Big Bang itself. This dual nature is the true story of the cosmic microwave background. It is a story of profound success, where a theory born from equations matches a snapshot from the dawn of time, and a story of even more profound mystery, where the map's quietest corners ask the loudest questions. The narrative is far from finished. With each new generation of telescopes, from the high deserts of Chile to the frozen plains of the South Pole, we turn more sensitive ears to the primordial sky. These instruments are not just collecting more data, they are learning to listen in new ways to the subtle curl of polarized light that may carry the signature of spacetime's first tremors. Every anomaly we have discussed is now a target, a specific question we are learning how to ask with greater clarity. Will they solidify into fundamental facts, or will they finally fade, resolved by data of unimaginable precision? Either outcome is a discovery. This ongoing quest is a testament to a simple, powerful truth in science. The more we learn, the more profound the mysteries become. You are witnessing one of the greatest detective stories ever told, a case that spans the entirety of space and time. The universe has left us a map written in the faintest whisper of heat and the subtlest alignment of light. We are only beginning to trace its contours, to learn the language in which our own origin story was written. If this exploration of cosmic beginnings has sparked your curiosity, we would love to hear your thoughts. What mystery on the map intrigues you the most? Share your questions in the comments below and consider subscribing to continue this journey with us to the very edge of understanding.